Okay, so power series. So never to be forgotten where they came from. They came from linear, quadratic, cubic approximations of functions, and furthermore Taylor series of Taylor polynomials of high degrees. When they're put together, they form power series. Okay, of a function, and then if the function is present, if it's not, then we're starting at the opposite end, which we were right now, starting with series, and then see if the series produce any functions, and they do. Okay, so and then so we're studying right now power series as functions, and specifically the simplest thing to ask about functions is what's its domain, and the domain is simply those x's for which the series converges. Okay, so if it does not, then it's not in the domain. So the function, that function given by the power series, is simply does not exist, and so it doesn't make sense, and we are not concerned about those values of x. Power series are especially simple ones. Their domains are simple. They are always intervals. So closed, open, half closed, infinite. There are only these three possibilities. Okay, so the examples are these. As the example of the illustration of the theorem is at the top. So good interval around A is where everything is good. Outside it is bad unless there is nothing to begin with, unless the interval is infinite, like this, like with the sine and cosine. The infinite interval is wherever you put your center will go both way to plus and minus infinity. That's what it means for a series to converge at every value of x. Just for completeness, let me give here my exponential function. 1 over k factorial e k. So the exponential function, once again, is convergent on the whole thing, on the whole real line. Okay, so recognizing one, we'll see how we can actually recognize a function behind a series. Right now we'll look at a different direction, and that is how to find, there is a trick, kind of a trick, to find sometimes, that's not right, to find, wait a minute, how do you spell trick? I need trick. Is it trick? Okay. A trick for finding power series representations. New power series representations from old. And the trick is pretty much just algebra. So we have these three representations. Okay, we had one more, as a matter of fact. So let me, for completeness of the list, sum k from 0 to n is equal to 1 over x plus 1, and this one is converted to negative infinity. I'm sorry, negative 1 1. Okay, negative 1 1. Okay, so this one is not infinite. It has two holes at negative 1 and 1, and outside it is bad. Okay, so the three are good ones, and one is only limited to an interval. Okay, so we can take the series and we can produce a series, rather a matching up of power series on the left and function on the right. We can do some algebra with them based on the fact that they're all convergent, and we'll get new functions, new series. It is as simple as, for example, multiplying by x. So let me copy this. Nope. Nope. Not doing too well. What's going on here? Let's maybe start over. Okay, so what I mean is, so I could just take either one of these series and multiply them by a number, or anything else, including x. Okay, so for example, I could say I put a 3 here and 3 there. Okay, so there we go. I have a power series representation of my of a new function. 3 sine x now have a power series representation. For completeness, I would only take this 3 and pull it inside in order for us to have the standard representation, standard way to represent a power series. But otherwise, you have a power series for a new function. Okay. Now I could multiply positive, negative number. I could add a number to which will only affect only the say like this plus 2. If I add plus 2, what difference does it make? It only makes the difference as far as the element of the term of my power series with k equals 0, because that's the only one that does not have x present. The rest of them have x present. They will be unaffected by this adding 2. So in fact here for cosine it starts with 1. So a naught will become, it used to be 1, it becomes 3. Okay, so let me just write it will be 1 plus 2. Okay, so that's the only change. So imagine that these elements of the series, of the second series, are spread out. If we're starting with 1, then skip, then it will be x squared with some coefficient, then x fourth, and so on. But if I add 2, then what effect does it have on the series? It only will change the very first term of that series. Okay, the very first zeroth term of the series. But the point being is that we're getting a new series, power series for a new function. Okay, so these are the two simplest ones. So adding a function, then I could add functions together. So like this. Okay, so I have two functions on the right, and if I want to add them together and find the power series representation of this new function, what do? I just add two series term by term. Okay, so just what we know about convergence of series. If we have two convergent series, we can add them term by term. So the result will be like this. So it will be summation k from 0 to infinity, and I have here 1 over k factorial plus 1. I'm sorry, this one is not e, this is x, right? It's power series times x to the k, and it gives me e to the x plus 1 over x plus 1. Okay, there you go. Fairly simple. New function, new series, made of all functions. The only question becomes, what is the domain of the new function? What's the domain of the new function? Well, we have two functions. Their domains are listed here. So we need to figure out what the domain of their sum is. So you should ask yourself, for what values of x the new series converges. What are those values? Well, if you want to guess, you guess one of the two. One of the two. Which one is it? The bigger one or the smaller one? What? So 1 is everything. For the my exponential function has the domain negative infinity to infinity, while the second one has the domain negative 1, 1. The sum of them, what is its domain, one or the other? The bigger or the smaller? Guesses?
The smaller one?
The smaller one. Why the smaller one?
The one function won't work with the bigger domain.
Yeah, so if we step outside of this smaller domain, let's say if we pick 2, x equal 2, we choose x equal 2, then even though the first series will converge, the second one will diverge. If we try to add them together, we'll realize that the whole thing also diverges. Okay, so we have to pick the smaller one. At least we guarantee that everything. When you have 2 divergent series, there is that 2 divergent series at some location, that there's a chance that they cancel each other and the result will be a convergent series. There's a chance of that, obviously. But in this particular case, one convergent, one divergent, which means that when you add them together, it will be divergent. Okay, so these are basic operations: constant multiplication, adding a number, adding 2 series. Okay, so also works out fine. What else? Let me multiply by x. Let me multiply by x. Let me so skip over to the next line and look at my exponential function again. 1 over k factorial e to x to the k. So it corresponds to e to the x on negative infinity infinity. Okay, and then what if I look at x e to the x? Okay, so x looks more complicated than just multiplying by 3, but it is, after all, is just a number. So it's not a series, so there is no term-by-term events. But rather, what is it? Well, it is a term-by-term event, but it is x is still a constant. So I'm looking at this series. I take my series and simply multiply it by x term-wise, and then what I'm supposed to figure out is a very simple thing: is what is the new power series. So this is right now what I have on the left is not the answer because it's not a power series yet. I have to put it in the standard form. So what do? I do the distributive property. In a way, it is I'm using constant multiple rule. The constant multiple rule, x is constant. You see, it's the constant in constant multiple rule refers to k. Okay, so x is constant relative to k, even though it varies as far as the x-axis is concerned. But if we're doing 1x at a time, this is totally legitimate to simply bring it in and to have this 1 over k factorial x k plus 1. Okay. So as you can see, since we're multiplying by x, what's going to happen to the series? There won't be a free term. So the very first term is 1 for the exponential function, gets multiplied by x, so it's x. That's the only difference. But otherwise we have a very cheap way to produce a new power series. Okay, which can be, by the way, rewritten just for convenience. We can start k from 1. Well, how about it's not k? How about it's m? Just to make that point clear, we are doing a power series, but since I want to correspond my powers to the terms of the series, so I start counting with power 1. So m starts from 1 to infinity, but the coefficient will be m minus 1 factorial. Okay, so I have produced a new series x e to the x by simple multiplication. So the second one is just as popular, I suppose, is substitution. So this is addition, multiplication, the usual operations of algebra, but the 4 operations of algebra. You can even divide if you want to. In fact, let me do the division. So this is multiplication. You can have division if it is at all can, but let's say not always. So what I'm gonna do is I'm gonna take the series for I'm gonna take the series for sine. You see at the top over there, what is so special about the series at the top is that its very first term is x. sine x, the power series representation of sine starts with x, and then the rest of them are higher degrees of x. If that's the case, I can divide by x, and I still have a power series right away without any effort. Okay, so that's what I want to accomplish here. Okay, so so this is my, let me erase this. Okay, sine x. That's also has to go. So this is what I'm going to do. I'm going to divide by x. I divide by x like this. So it is a constant multiple idea, just as before, but just as in the last example, it's a slightly more algebra for us to worry about, because you might, if you apply this to the exponential function, think about it, what's going to happen if I started with this one. If I started with the exponential function, and instead of multiplying by x, I divide by x. What's going to happen? The very first term of the exponential function power series is 1. So when I divide by x, I will end up with 1 over x, and that is not power that we can have in a power series. So then we would have to, that whatever you get is not going to work as a power series. You've got to do something else. Here, however, everything works out just fine. I can factor it in, and I have summation k from 0 to infinity, -1 k to k plus 1 factorial, and I have simply x to k. There you go. I start with sine x divided by x, and I ended up with a new power series. There is no division, right, because when k is equal to 0, the power will be 0, it's fine. And so that's a power series which happens to be, in fact, an even function, and even only has even terms, even powers. And no surprise, that's what it is. The sine x over x is an even function. It has a power series representation with only even series. Okay, one more example is the substitution. Okay, so I'm taking the power series for the exponential function again. Okay, so that's my power series, and then what I do is, what if I need to power series representation of ex squared instead? Well, it's very simple, right? I just take that series that I already have, and I replace each x with x squared. Right, so that's what has happened here. X turns into x squared. I do the same thing in my power series. Just substitute x with x squared. X squared. It is pure substitution. Okay, so which is still not quite power series representation, but I can I use the exponential formulas for exponents, and I have x 2k like this. Okay, so that is indeed a representation. In fact, it looks a little bit like the power series of the of cosine, except it has more terms. This one does well. Actually, it has only even terms, right? This new series has only even terms, and the function is even indeed. It is not. It is so just like the power series of cosine. It has only even terms. The difference is the coefficients. The coefficients will be, as you can see, are somewhat different. Okay, so so that's these are kind of tricks of the trade of what you can apply if you're looking for power series representation of a new function. All the algebra, not all the algebra, but quite a lot of algebra of functions is transferable to the algebra of series, and then whatever's happening in this part of the table, the function will happen with the power series on the other side of the table. So like two columns, series here, functions there, and I do algebra with both of them. Okay, so that is certainly our well, that certainly tells us already a lot about power series. They are just as good as a series. That's the I guess the take-home idea that we're going to develop a little bit more is that power series of functions, but in fact there are just as many power series as functions, almost. And for many purposes, power series are better than for the function that we know. At the very least, we have all the familiar functions. We have represented them by power series, and then, well, that's a starting point. The only thing that we need to make sure that we understand, and that is about this correspondence, and it is the uniqueness of power series. What it means, what I mean by that is that there is only one power series for each function. Okay, so we have not explained that, but it is kind of in the background, and it is presumed for the theory that we have in mind to work. They have to match. Function series have to match, and you should be able to go back and forth, and you should not be confused by having different representations for the same function. Okay, so it goes roughly like this. If two series are equal as functions, on an open interval. So that's a crucial condition in the open interval. Functions are equal on an interval rather than in one point. If they coincide in one point, then we cannot say anything useful about them. But if they coincide on an interval, like so, in other words, like this. I know, like this. Maybe. So that's one function here, and the other function is there, and they have a piece in common. A piece in common, not a point, a whole piece. Then it's the same thing. So they cannot split up. If they have a piece in common, they cannot split up. So let me finish the statement. On an open interval, then their corresponding coefficients are equal. So let's put it this way: sum Cn x minus An, and from 0 to infinity, is equal to sum Dn x minus Anth power n from 0 to infinity for all x in an interval, say a minus r, a plus r. Okay, like this. So as long as r is positive, we have an interval of non-zero length, and that is sufficient to compare two series. Okay, so even though both series might be convergent on a full bigger interval, maybe infinite interval, but we're comparing them only on a piece like this. So this is what I'm talking about, like this. Okay, so this is my x-axis, and we have a plus r, a minus r, and these two coincide on that piece. Whatever is happening outside, we don't know. That doesn't matter. Turns out it doesn't matter. Then, what is it? Cn is equal to Gn for all n. Okay? So it is the same power series. So the coefficients are the same, so it's the same power series. So, this statement requires a bit of a proof, and it's not a hard proof. All we have to do is just to do some substitution. So equal, by the way, I'm not sure if it is entirely clear, but they are both convergent. Because if they don't converge, one of them doesn't converge, they cannot possibly be equal because they simply don't exist. You can compare things that don't exist. Okay, so Cn is equal to Dn. These are two the same series. And the result is a bit surprising because if you think about it, about the intuition for functions, think about it. So I have a function like this. So suppose I drew a function like this. It's a graph. It is entirely within my power to continue drawing it any time, any way I want. Right. So suppose I drew my graph to this. I can continue this way. I can continue that way, or this way. It's entirely within my power. Infinitely many possibilities to draw a same starting point on the left. Okay, so this is my starting point. This is my graph. Okay, and then I'm creating a function, a bigger function, more and more. Okay. Well, it turns out that is wrong. I'm not it's not freely in my power to continue function any way I want if I want this function to be differentiable, twice differentiable, three times differentiable. Okay, so the continuity, the differentiability conditions will force a function to behave one particular way. So if you know your derivative, at this point over here, it will tell you everything about the behavior of the function elsewhere. So all the derivative, and that's what the power series is. It is in fact, remember Taylor polynomials. All these coefficients are in fact nothing but derivatives of your function hidden. Okay, so if you know all the terms, coefficients of your power series, then you know all the derivatives. And if you know all the derivatives, it turns out that the freedom of drawing of any function you want is restricted entirely. So if you have a piece of the function, then you know the rest of the function as well. Okay, so it is. You can see why it is the case by analogy. If you think about it, if your function happens to be linear, then you can ask yourself, am I free to continue function any way I want? And the answer is not. No, you cannot. There's only a way to continue a linear function, like it is like this. If you have a quadratic function and their second derivative, first and second derivative are determined, then once again you cannot freely continue on from this point in any way. There are infinitely many parabolas here, but through that point, but only one is legitimate. It is the one that has the same first derivative and the second derivative. Okay, so that is something that you discover from studying power series. But why it is the case is needs to be explained. It is explained by continuing on with theory, and that theory is calculus of power series. That is pretty much the high point of the class, I think, of the calculus of power series. So all of this, not for nothing, build up of the theory. Kind of complicated, but now at least we have something that that is just as good as functions. In fact, it is better. It is better because so all familiar functions are represented by power series. But then if we have an unfamiliar function, that's okay too. It also has a power series. Whether or not we have a power series, we can find a function for it is secondary, because power series will give us everything we want. If you need to compute the value, you plug in the value. You can have it with any accuracy that you want. That's the series converges. You can also differentiate and integrate it. That's what the next topic is. What do we do with the series as functions? Same things as we did with functions. We can differentiate them and we can integrate them. And the way it works out is really simple. Let me just give you an example of how calculus of power series works out. So I start with my power series of the exponential function, and what if I differentiate it? So suppose we don't know about the derivative of the exponential function. So then naturally, without trying to justify this yet, but how would you differentiate this thing on the right? You would differentiate it as one by one, right? How else would I differentiate? So if I'm thinking about the derivative of the exponential function, I start differentiating these term by term. So 1 prime plus 1 over 1 x prime plus 1 over 2 factorial x squared prime plus 1 over 3 factorial x cubed prime, and on and on. Okay? And at that point you will see a pattern. This is 0, this is 1, this is 1 over 2 factorial, so it will be 2 times divided by 2 factorial x, okay? Then it will be 3 over 3 factorial x2, right? Then it will be 4 over 4 factorial x cubed, and on and on. So if you had an nth term, 1 over n factorial xn, and I differentiate it, what's going to happen? What's going to happen is, if this is prime, I will have n over n factorial x n minus 1. Okay, so that is term by term differentiation. And you can see how easy the differentiation is, because what are the terms? They are power functions. So all you need for differentiation of power series is the power formula, right? So which is what I just did. So x squared derivative is 2x. Derivative of x cubed is 3x squared. Derivative of x fourth, 4x cubed, and so on. Okay, and now I start canceling things out. So I'll have 1 plus 1 over 1x plus 3 divided by 3 factorial. It will be, you remember what factorial is. It's all the number through n. So here it will be 2 times 3, and I'm left with, what's the denominator? 3 over 3 factorial is 3 divided by 2 times 3. 3 is gone, and I have 1 over 2. 1 over 2x squared. The next one is more interesting, because it will be 4 over 4 factorial. What is it? It is 4 divided by 1 times 2 times 3 times 4. 4 cancels out, and I'm left with 1 over 1 times 2 times 3, which is 3 factorial. Okay, so we have in fact 1 over 3 factorial x cubed, and on and on. So the last one is especially clear. It will be n over n factorial, so it will be 1 times 2 times 3 times n minus 1 times n. We cancel n, and we are left with, once again, a 1 over n factorial right here. So this is the term 1 over n factorial x. I'm sorry, 1 over n minus 1. Yeah, 1 over n minus 1 factorial over here. Okay, so did you follow what happened? Right. So that extra term that comes from differentiation of a power function is used to cancel and move from n factorial to n minus 1 factorial, and that happens in every single term. And then we end up with what? Degree lower by 1 each term, but that's what happened if you go vertically here. If you go vertically like this, you can see how the power went down by 1, as well as the factorial in the denominator also went down by 1. Okay, and at this point, what do? We'll look at what we ended up with. What did we end up with? Look at this series. What do we have? It's the exact same we started, right? So 1 and 1. This one matches, and this one matches, and whatever. This one matches too. Okay, so we match them. We kind of, what has happened is a shift, right, like this. A shift to the right, because the first term disappeared, it is 0, but the rest of them are kind of shifted through this differentiation, and that is a major recognition for us to recognize, indeed, that the derivative of the exponential function is the exponential function. Okay, so we still need to justify it, but at the very least you can see what can happen. And this probably is the hardest part, is recognizing power series as something familiar. But that's a bonus. Even if we imagine that it wasn't, we did not do the last step. We just did not recognize the exponential function there. Is it such a bad? Is it such a disaster? No. We still have a power series representation of that derivative. We can still find its. It is a function. We can find its values with any accuracy that we want, and then if this theory works out, I can take that function, which does not have a formula. I can differentiate again. I can integrate again. I can do algebra with it, add, subtract with other series, multiply by functions, and so on. Okay, so even if the last step did not work out. Okay, ideally, and that's a good example just to confirm that we are moving in the right direction, is that indeed match up the series with familiar functions, including, let's not go through the whole thing, but if we just go back to power series representations of these basic functions, you can recognize what can happen. So we did the example that we carried out was at the top. I'm sorry, not at the top, but rather over here with the exponential function. But you can imagine if we look at the one at the top, sine. Okay, imagine differentiating term by term. What's going to happen? Term by term, which means that you could kind of ignore the sigma and just do differentiation inside of each of the terms. So what's going to happen to x2k plus 1? What? Pretty much the same thing, right? What? So, well, if I take this thing, so, where is it? Where am I? Here, right? And okay, so suppose this is my series. Once again, I don't want to go through the whole thing, but you can just imagine what's happening if I start differentiating this term by term. Summation, we keep the summation intact. What's going to happen? Let's differentiate. What do we get? So I keep this constant multiple rule. This is unaffected. And then what's the derivative of x2k plus 1? Power formula, right? So what is it? Differentiate this. K plus 1, right? 2k plus 1 multiplied by x2k. Okay, so then as you can see, that once again we have this matchup, which we can cancel, and my factorial goes down by 1, and I have negative 1k, 2k factorial, x 2k. Okay? And then, so, well, whether or not this works out, it's we have a new formula on O series, we have a new series, but if we remember where this came from, this one from sine, and then we recognize this as cosine. Okay, so once again, it works out as planned. One time when this does not work out fully as full transition, function series, differentiation, new series, old new function. Okay, so that's the three-step procedure here. So once again, function is sine. We get a power series for it. Then we differentiate the power series term by term. We get a new power series. We rearrange terms simplified, and we recognize a new function which is cosine. Okay, so that's a full operation that worked out twice. When sometimes it does not work out, but they are just as important, if not more important, examples, and that is this ex squared. Well, what I'm trying to say is why this is important. First of all, we have a power series representation for it, and remember with nothing but substitution, so 1 over k factorial x2k, yes. Okay, so that's power series representation of this function. This is a very important function, and it is known as the bell curve. Okay, so that's what it looks like. It appears in all probability and statistics as the normal distribution. It is given by the formula ex squared, negative x squared, okay, which difference is negligible, with a certain coefficient in front of it, but essentially the function is close enough to, I just simplified that normal distribution function in order to concentrate on what we care about. And then why is it important? Because it is the most common distribution of random quantities in the whole, well, in the not just in the probability, just everywhere you look, you see these distributions. So it is distribution of heights, distribution of grades, distribution of IQ points, of prices, of weights of people. They all distribute in roughly that manner. Incomes, whatever. Well, maybe not incomes, but in many examples. Shooting at a target at random will produce this pattern, once again, dense in the middle and sparse as you move away from the center. So it's a very important function, and yet there is no, not this is important, this is an important function, but why we care is this, because we need to compute, we might need to compute this. The area under the graph might be needed to be computed in order to evaluate the probabilities of certain events. So in case of shooting at a target, and suppose you know that your theory is that your placement distributed randomly, then you might ask yourself, what is the probability that you say hit a bullseye? Okay, so it means that you limit your attention to a smaller piece of the target, and then you integrate over that region. So in this particular case, it's an integral, so it's entirely then understood in calculus 1 terms, and we need to evaluate this area, which will give you the probability of what? Of us being here. So how likely do we hit this target over here? So either it is a probability of hitting a target, a bullseye of 9, 8, and so on, as well as a probability of, say, heights of people of this age being within this interval of heights between, I don't know, 5 feet and 6 feet high. Okay, so all that requires what? It requires integration. So we need to integrate. Okay, so we need to integrate what? The distribution formula, right? That's, remember, that's how we find areas, and then unfortunately that's the problem, that this function is not elementary. It is what's called a special function. So it's not on the list of the functions that we know. No, we can combine it from the old functions. Okay, so the only way to deal with that function, the new function, the integral of the old function, e to the x squared is familiar function, right? It's just composition of two functions, but however, its integral is not anymore. So what to do? Now we have the answer, and it is simply the answer is to integrate term by term. So we just did differentiation term by term, and now we can also integrate term by term. So integral ex squared dx then is integrated term by term, if we can do that. Integral 1k factorial x 2k dk dx. Okay, so term by term integration once again is very easy because we have nothing but power functions. So once again, just like with differentiation, nothing we need to do here but to apply the power formula, right? So 1 over k factorial is out, and then when I integrate x to k, the power goes up, right? So I'll have x 2k plus 1 divided by 2k plus 1. Okay, so we have a new power series which happens to be an antiderivative of that function that is unspecified. So once again, we do not start with any sine, cosine here or any other function. It is an integral of a familiar function, but the function itself is not familiar, and so then we are not, we don't hope to end up with anything familiar, but we do end up with a new power series, and this power series is as good as everything else because we could it converges, and it it can be computed with accuracy that we want, with any accuracy that we want. So once again, at the beginning is the integral of a function that is familiar, but the end result is we stop here. We do not continue on because this is there is no familiar match for this function out of any that we have seen. And so we just take it as it is. It is a power series, and so we just take it as a representation of a function that now we can compute it with any degree of accuracy. We can differentiate it, we can integrate it, we do algebra with it, and that we just satisfied with that. And in particular, it is you'll find this function in every textbook of probability, and it is in every calculator as well. ERF, as I believe it stands for what it stands for. Okay, so so we'll wrap this up tomorrow.